In Chapter 2, we studied one-dimensional motion with constant acceleration. With a slight change in notation, we repeat the equations obtained there for an object whose motion is restricted to the x-axis. That is, ax equals, say, constant 1, vx equals vx0 plus axt, x equals x0 plus vx0 t plus 1 over 2 ax t square. Vx square equals vx0 square plus 2ax times x minus x0. Here the subscript x in ax, for example, indicates that we are considering the acceleration in the x direction. Similarly, vx0 corresponds to the initial velocity in the x direction. We now consider a general 3D motion with constant acceleration. Say a equals constant. With constant acceleration, we mean that all the three components of the acceleration vector are constant. That is, ax also constant, say constant 1, ay equals constant 2, and az equals constant 3. This, in turn, means that both the magnitude and the direction of the acceleration vector remain constant at all times. It is an empirical fact that the complicated 3D motion of an object with constant acceleration can be simplified considerably by analyzing the motion for each dimension separately. In other words, part of the motion on an axis does not have any influence on other parts on the other axis. This fact is actually a direct result of the so-called superposition principle, which we will mention again in the following chapter. Therefore, we can write sets of equations for the parts of the motion on the y and z axis. Just similar, and in addition to that we wrote for the part on the x-axis, we say that ay equals constant 2, vy equals vy0 plus ayt, y equals y0 plus vy0 t plus 1 over 2 ayt square, and vy square equals vy0 square plus 2ay times y minus y0. And also az equals constant 3, vz equals vz0 plus azt, z equals z0 plus vz0 t plus 1 over 2 az t square, and vz square equals vz0 square plus 2az times z minus z0. It is the power of mathematics that these three equations in these sets can be written succinctly in vector language as a equals constant, v equals v0 plus at, r equals r0 plus v0 t plus 1 over 2 a times t square. Where v equals v of t is the velocity of the object at time t, v0 equals v of 0 is its initial velocity at t equals 0, r equals r of t is its position at t, and r0 equals r of 0 is its initial position at t equals 0. Okay, this is the end of the discussion of motion with constant acceleration in three-dimensional concentration. The next topic is the projectile motion, that is, motion with constant acceleration in a plane, that is, in two-dimensional space. The word projectile is a generic name for an object which is projected or fired or launched from a mechanism such as a gun, weapon, or catapult, flies through the air and maybe lands some distance away. Three reasonable assumptions facilitate the analysis of projectile motion. 1. The Earth is assumed to be flat over some small horizontal range of the projectile. This assumption is valid if this small horizontal range is much less than the radius of the Earth. 2. Air resistance is neglected. This is the weakest assumption to validate. Most of the time, we cannot ignore air resistance, but its inclusion makes it difficult to analyze the motion. Nevertheless, if the projectile does not fly too fast, the neglect of air resistance is a fairly legitimate approximation. And most importantly, 3. The projectile motion is assumed to be subject only to gravitational force, which results in a constant downward freefall acceleration of magnitude g equals 9.18 meters per second square. With constant freefall acceleration, we mean that we neglect the variation of g with altitude, which is reasonable if projectile motion takes place near the surface of the Earth. Under these conditions, projectile motion takes place in a vertical plane. Throughout this chapter, we assume that the projectile motion under question will be on the vertical xy plane, with the x-axis being the horizontal direction and the y-axis being the vertical direction. This means that the horizontal velocity of the projectile remains always constant, being equal at any time to the initial velocity. That is, Vx equals Vx0 equals constant. The sole vertical acceleration is always downward. It is convenient to write it as Ay equals minus g equals minus 9.80 meters per second square. It might be useful for a diligent student to note that the projectile's acceleration can also be written in the vector form as vector A equals g times minus j hat equals minus g j hat. With these choices, the set of equations developed in the preceding discussion will take the following general form. Ax equals 0, Vx equals Vx0, x equals x0 plus Vx0t, Ay equals minus g, Vy equals Vy0 minus gt, y equals y0 plus Vy0 t minus 1 over 2 gt square. Here, since there is change in the vertical velocity, we have Vy square equals Vy0 square minus 2g times y minus y0. Okay, let's solve an example of projectile motion, which is symmetric projectile motion. We now analyze the symmetric projectile motion as an example. We mean with symmetric that the launching and landing points of the projectile are on the same horizontal line or surface. In the following, we will prove that the y direction of the position vector is y equals tangent theta 0 x minus g over 2 times v0 square times cosine theta 0 square. The whole thing is multiplied by x square. This is called parabolic trajectory. And the maximum altitude h max is v0 square sine theta 0 square over 2g. And the horizontal range is r equals v0 square over g times sine 2 theta 0. Okay, let's try these formulas in the following discussion. As in this figure, taking the origin of the xy plane as the launching point will simplify a bit the redundant notation. You can always make the launching take place at the origin with a suitable change of coordinates. Then we have x0 equals 0 and y0 equals 0 right now. Let the projectile be launched with an initial velocity v0, which makes an initial angle theta 0 with the positive x-axis. We have v0 equals vx0 I hat plus vy0 j hat, where vx0 and vy0 are the respective initial speeds in the x and y directions, which are found from this figure as vx0 equals v0 times cosine theta 0 and vy0 equals v0 times sine theta 0. Now, there are only two equations that govern the motion on the horizontal x direction. The first one is Vx equals Vx0 equals V0 times cosine theta 0, which is constant. The constancy of the horizontal velocity is clearly illustrated in this figure. The second equation gives the x-coordinate of the projectile. That is, x equals x0 plus vx0 t equals 0 plus v0 cosine theta 0 t. Then we say that x equals v0 times cosine theta 0 t. There is nothing special about this result. Since v0 and theta 0 are constants, this equation tells us that the projectile's x-coordinate increases linearly with time t. The projectile's vertical motion can be analyzed by three equations. The first two are for the vertical speed. Vy equals vy0 minus g times t, that is, Vy equals v0 times sine theta 0 minus g times t. Here, the result tells us that the vertical speed Vy, which has an initial positive value Vy0 equals v0 sine theta 0, decreases as time goes on with the constant acceleration minus g. Then it becomes 0 at its highest point, and then it reverses its direction towards the Earth. That is, its numerical value becomes negative. the magnitude of this negative value increases with time at every moment, and the projectile hits the ground with the same vertical speed as its initial vertical speed. These are all markedly shown in this figure. The second equation relates the square of the initial vertical speed to that of the vertical speed at any later time. That is, Vy square equals Vy0 square minus 2g times y minus y0 equals V0 times sine theta 0 square minus 2g times y minus 0. The result is Vy square equals V0 times sine theta 0 square minus 2 times g times y. For the projectile's position in the vertical direction, we have y equals y0 plus Vy0 t minus 1 over 2 times g times t square, and it is equal to 0 plus V0 sine theta 0 times t minus 1 over 2 times g times t square. From the equation for x, that is x equals V0 cosine theta 0 times t, we obtain t equals x over V0 times cosine theta 0. Substituting this into the equation for y, we get y equals V0 times sine theta 0 times x over V0 times cosine theta 0 minus 1 over 2 times g times x over V0 times cosine theta 0 and square of the whole thing. Whence y equals tangent theta 0 times x minus g over 2 times V0 square times cosine theta 0 square, and the whole thing is multiplied by x square. Here the expressions inside the parentheses are all constant: g, v0 and theta 0, so that this equation is of the form y equals ax square plus bx, which is an equation of parabola passing through the origin. In other words, the path of a projectile is a parabolic trajectory. At the instant the projectile's vertical speed Vy is 0, it will be in its maximum height called hmax, as shown in this figure. So, equating the equation for Vy to 0, we find the time Tmax required for the particle to reach its maximum height. Namely, Vy equals 0 equals V0 times sine theta 0 minus g times Tmax. Then, the result for Tmax is V0 times sine theta 0 over g. Plugging this result into the equation for y, we obtain y equals hmax equals V0 times sine theta 0 times Tmax minus 1 over 2 times g times Tmax square. Putting the value of Tmax here, we obtain V0 times sine theta 0 times V0 times sine theta 0 over G minus 1 over 2 times G times V0 times sine theta 0 over G, and the square of the whole thing. This leads to the maximum height for this symmetric projectile motion, such that H max equals V0 square times sine theta 0 square over 2G. In this figure is also shown the horizontal range R of the projectile, which is the horizontal distance between the launching point, that is the origin, and its landing point, whose coordinates are xy equals r0. We see that the time tr required for the particle to reach this point is twice the time t max required to reach its maximum height. This means that tr equals 2 times t max equals 2 times v0 times sine theta 0 over g. Insertion tr into the equation for x results in the particle's horizontal range as x equals r equals v0 times cosine theta 0 times tr, which is equal to v0 times cosine theta 0 times 2 times v0 times sine theta 0 over g. Then we obtain 2 times v0 square times sine theta 0 times cosine theta 0 over g. Since 2 sine theta 0 times cosine theta 0 equals sine 2 theta 0 from the trigonometric relations, we write the expression for r in a more concise form as r equals v0 square over g times sine 2 theta 0. Don't forget that this result is valid if and only if we have a symmetric projectile motion. If the launching and landing points are not on the same horizontal level, you cannot use this result. This expression for r has two important consequences. The first one is that r is maximum when sine 2 theta 0 equals 1, which amounts to 2 times theta 0 equals 90 degrees, or theta 0 equals 45 degrees. The second consequence follows from the expression sine 2 theta 0 equals 2 times sine theta 0 times cosine theta 0, which tells us that for the two complementary initial angles, that is angles which add up to 90 degrees, say 30 degrees and 60 degrees, we have the same sine 2 theta 0 values because sine of the angle 30 degrees equals cosine of the angle 60 degrees, and vice versa. We then draw the conclusion that two complementary initial angles give rise to the same horizontal range r for a symmetric projectile motion, as is shown in this figure for the theta 0 equals 30 degrees and 60 degrees. Okay, we have derived all the formulas for y, h max and r. Then comes the last topic, uniform circular motion. If If an object orbits a fixed point at constant or uniform speed, it is said to be in uniform circular motion. Although its speed v is constant, the velocity vector v of the object does change because its direction changes continuously, as is seen in this figure. Since acceleration by definition is the change in velocity vector v in time, the object does continuously undergo an acceleration. Out of its importance, it is convenient to state first the underlying properties of uniform circular motion. Uniform circular motion takes place in a plane so that it is a two-dimensional motion. The path of the object might also be a circular arc, not necessarily a complete circle. The speed v of the object is always constant around its circular path. The velocity vector v of the object is everywhere tangent to its circular path. The acceleration a of the object is everywhere perpendicular to velocity vector and is always directed to the center of the circular path. In other words, a is radially inward. Because of this, the object's acceleration AR, is called radial acceleration or frequently centripetal acceleration. We shall show shortly that the magnitude of this radial acceleration is given by A equals AR equals V square over R, where V is the speed of the object and R is the radius of the circular path. You can easily verify that this expression has the correct unit of acceleration, meter per second square. If the object's path is a complete circle, its acceleration vector has no component along its velocity vector. That is, there is no tangential acceleration vector, namely at equals 0. We call the time T required for the object to complete one revolution as the period of the motion. Since the object travels a distance of 2πr in one revolution, it follows from the definition of speed that v equals 2πr over t, or t equals 2πr over v, which is in seconds. Let's now prove that acceleration vector A is directed toward the center of the circle, and that its magnitude is given by A equals AR equals V square over R. To do so, we will use this figure, where the object is at position 1 at time t1 and at position 2 at a later time t2. The object's velocity is v1 at 1 and v2 at 2, with the speeds v1 equals v2 equals v. That is, the object's velocity changes only its direction while its magnitude remains constant. The average acceleration of the object when it goes from position 1 to position 2 is vector A average equals delta V over delta T equals vector V2 minus vector V1 over T2 minus T1. We are then required to determine delta V equals V2 minus V1, which we have performed graphically in the vector triangle shown also in this figure. We notice immediately that delta V is directed toward the center of the circle. This conclusion is also valid if we let time delta t be infinitesimally small. To determine the magnitude of vector A average when delta t goes 0, we write the magnitude of the first part of the preceding equation as A average equals delta V over delta t. This figure shows two congruent or similar triangles. One on the left with sides delta S and R, and one on the right with sides delta V and V. The congruency condition gives us delta S over R equals delta V over V, or delta V equals V over R times delta S. With this result, we have A average equals delta V over delta T equals V times delta S over R over delta T. In other words, V over R times delta S over delta T. We then take the limit of this expression as delta T goes 0. This means that distance between positions 1 and 2 is infinitesimally small. In this limit, the ratio delta S over delta T approaches the speed v of the object, and the average velocity vector A average approaches the instantaneous acceleration A, which is the centripetal acceleration AR of the object. Mathematically, limit delta t goes 0, A average equals A equals AR equals limit delta t goes 0, V of R times delta S over delta t, and V over R times V. So the result is V square over R, which is what we set out to prove. Very good. This is the end of chapter 4. Thank you for your listening, and see you in the next chapter.